Hello and welcome to North Country Community College. This is Intro to Math Concepts and my name is Lee Susi, so hopefully you're in the right spot. But if not, well, you can stop the video and start looking someplace else. Anyways, hopefully you are in the right spot though. And we're going to jump right into the new material. So hopefully you have the lecture notes, which if you open up in there, this should be one of the first pages in those notes. Now, we're not starting with chapter 1 or chapter 2. We're going to jump right up to chapter 6, which actually gets into some of the basics that hopefully you remember a little bit about. But if not, it's okay because you'll pick it up pretty fast. So this first section, 6.1, is looking at the real numbers, order, and absolute value. So the first thing that we're going to go through is all the different types of numbers that are out there that we're going to be dealing with. So the first group of numbers is the natural numbers, and that's just your standard counting numbers. So it starts at 1, and it goes in increments by 1 forever and ever. So the 3 dots are that indicator. So anytime you see those 3 dots, that means it just keeps going forever and ever. So another way to phrase it is, and so on. So that's one way you can describe that. So that's the first group. The next group up from that would be the whole numbers, and that is very similar to the counting numbers, but it starts at 0 instead, and then it increments by 1 forever and ever. So those two are pretty standard groups of numbers. They're positive numbers. The next group after that, though, is the integers, and the integers now start to include the negative counting numbers. So 0 is going to be in the middle. We got our positive counting numbers on the right. We got our negative counting numbers on the left. And all together that forms the integers. So those ones aren't too bad. Now it starts to get a little bit messy after that. The next group of numbers is called the rational numbers. So now some of this notation is kind of funky, but mathematicians use shortcuts anywhere they possibly can. And this is where they would do that. So this says the set of all numbers x. What's x? Well, we'll talk about that. The set of all numbers x, this vertical line means such that. So the set of all numbers x such that x is a quotient of 2 integers with denominator not equal to 0. Now, what does that make you think of? Hopefully the word denominator kind of gives it away. So if you hear the word denominator, hopefully you're thinking fractions. And that's essentially what the rational numbers are. They're looking at all the different possible fractions, and we can't have the denominator equal to 0. So the denominator, remember, is the bottom of the fraction. So we can't have the bottom equal to 0. So we could have something like 1/2, we could have 3/4, we could have 100 over 101, but we could also have improper fractions. So these ones are all proper, but we could have improper ones as well. So you could have, 200 over 38. That would be a fraction, so that would be considered a rational number. So any number we can think of that we can write as a fraction has to be rational. But what about some of these previous ones that we just talked about? Could we write those as fractions? The answer is yeah. So if we wanted to, we could have said, okay, I'm going to put 2 over 1. 2 over 1 reduces down to 2. So that would also be considered a fraction, so it must be a rational number. And we can do that with any of these numbers up here. We can put them all over 1, and that makes them rational. So you can kind of see that these first 4 layers of numbers all build upon one another. So you use the first group in the second group. The second group gets used in the third group. The third group gets used in the fourth group. But once you get to the rationals, that's where it stops. So after the rationals, now we're going to look at a whole other realm of numbers that are going to be irrational. So if they're irrational, this means that it's a real number as opposed to a false number that is not rational. So now the question is, what numbers could that be? Well, I'll give you a hint. What about something that looks like that? You know what that means? Anytime you have this type of symbol, that means you're talking about square roots. Square roots are a whole realm of numbers that are going to be irrational for the most part. Not all of them though. Now why is that? Well, what this actually means is it wants to know a number that when you multiply it by itself, you get that answer back. So the answer for this one is a long, crazy decimal. 1.4142135, and it just keeps going on and on and on. There's no real pattern to it, and so that is why it's an irrational number. We're going to get to the actual definition for it a little bit later, but for now, if we multiplied 1.414 for short times 1.414, we're going to get a number that is pretty close to 2. It's probably going to be something like 1.9996 or something like that. It's close, but the more decimal places we tack on, the closer we're going to get to that 2. So that's why it's irrational, because again, it goes on forever and ever. But are all square roots irrational? Well, hopefully you know a couple that aren't. What if we looked at the square root of 3? Well, square root of 3 turns out to be 1.7320508, and it goes on forever and ever. But what about the next one? Square root of 4 is equal to 2, because 2 times 2 is 4. So there are some cases of square roots that are going to turn out to be rational. So, and we're going to explore those later on, but we do got to be careful. So we can't just blanketly say that all square roots are irrational. No, that's not the case. So we're going to keep an eye out for some of these special cases as we go. The last group of numbers we're going to look at is the real numbers, and that is a simple one. It says the set of all numbers x such that x is a point on the number line. So if you were to draw a number line, every single point on it has a numerical value to it. So that means that all of those numbers are real. So there's a little bit of a number line, and again, it goes on forever and ever. But if I wanted to say 1, obviously that has a spot right here. If I wanted to say -2.5, well, -2.5 should be right about there. So there's -2.5, 2.5. Now, another number that you might know that's irrational, which I didn't talk about, would be pi. Pi is a very special irrational number. So 3.141592, and that goes on forever and ever. So pi is important when it comes to geometry, and we're going to see that again later on in the course. So, but pi has a spot on the number line. So pi would be right about in here. 3.14, so there's pi. So pi must be real as well. So it turns out that everything we've talked about here has to be real. So that's nice. So the question you might say is, well, aren't all numbers real? Well, that's a funny question, because there's a whole realm of math that talks about imaginary numbers. And then when we mix imaginary numbers and real numbers together, we get a whole realm of mathematics that talk about complex numbers. So that's way out of the realm of this course, and we're not going to worry about it. So, but there is much more stuff that you could do with imaginary numbers. So, okay, so now that we have a little bit of a basis on what types of numbers we have out there, let's look at an example that kind of culminates all of this. So they're giving you a group of numbers to start with, and they want you to just identify them in the right spots. So we got -9, negative square root of 7, -1.25, -3/5, 0, square root of 5, 3, 5.9, and 8. Now don't let those curly braces throw you off. All that just means is that you have a group of numbers. And that's what we saw up above. It was just a group of numbers. It's not anything fancy, so don't let it throw you off. But now, looking at this group of numbers, which ones of those would we consider natural? So if we go through them, we can kind of see, okay, natural, remember, is counting. So, well, 3. 3 is a counting number, and 8 is a counting number. So both of those we'd want to write down as natural. For whole numbers, okay, that's the next step up. So we do have 0 in here, so 0 would be a whole number, but so is 3, whoops, and so is 8. So all three of those numbers we'd want to write down as whole numbers. And so you can start to see the pattern here. So now, remember, it keeps building off the previous one. So all of these numbers that we just wrote for whole numbers better be integers as well. But are there any other ones? Well, -9. -9 is a negative counting number, so we want to include that. And there's nothing else in here that's a counting number, so we're just going to have those 4. All right, remember, rational numbers are fractions. So fractions, okay, well, but remember, all of these integers we can write as a fraction if we put them over 1. So we got to include those. So now I'm nerdy, so I like to go from left to right. So let's see. So what about negative square root of 7? Would we want to write that one down? No, that's no good. So what about negative 1 1/4? Hopefully you're going to say, yeah, that's got to get written down. So we got that one. Negative 3/5, yep. 0, yep. Square root of 5. No, that's not going to be a nice number. 3, yep. Now what about 5.9? So remember, the question you have to ask yourself is, can I write it as a fraction? Well, yeah, sure, why not? I can write 5.9 as 5 and 9/10. So there's a fraction, so that means we got to write it down. Now, not all decimals are going to be rational. Remember, up above, we said that there's some yucky decimals that won't be considered rational. So we're going to keep an eye out. We're going to explain that in a little bit more detail once we get to later sections. Now, the last one there is 8, and we know that one's got to go in. So now that you have all the rational numbers identified, the only thing left for irrational is what you didn't write down. So what are the ones you didn't write down? Well, negative square root of 7, square root of 5. So those are the only 2 that we got to write down as irrational. And then for real numbers, we can be lazy. We said all of them. All of them. Irrationals and rationals all have a spot on that number line. So they all fit. Not too bad, right? Okay, let's try a different angle. Just decide whether each statement is true or false. Every natural number is a whole number. So no matter what natural number I think of or that you think of, it's got to get folded into the whole numbers. Well, we said that before. All the naturals get folded into the wholes. All the wholes get folded into the integers. All the integers get folded into the rationals, and that's where it stops. So in this case, the answer is true. Every natural number has to be a whole number. What about the next one? Every rational number is an integer. So now we're going to decide if that's going to work. Well, does every integer fold into, every rational number fold into the integers? Well, no, we had some weird examples up above, so that's got to be false. Okay, so again, I don't want to make these videos too long, so we're going to stop there, and then we'll pick up the rest of this in the next video. See you in a minute.